it won't verify the function, but it will discover only the defect. So the manufacturing defects is like you have a deformation of the wire because of the electromagnet is that in electro migration, yeah, electromigration, electromigration. So over time, even like let's assume that we have a oh sorry, I didn't share yet, right? Let me share. Here goes. Okay, all right, let me restart. Not much. Okay, that's yeah. I just let's start with this. So we have a tree. So this DFT is to discover the manufacturing defects, which is like the yeah, is the physical defect. It's different from the formal verification or functional verification, which is check, assuming every connection physically is correct. Now we check if the design is correct. If the design meet the requirement or like meet the functionality we intended to. That's a functional test. This one is to test the defects, which is the physical. And then there's a two thing is a DFT, and we have the Stuckett model and the scan method. Okay, we back here. So even like let's assume that because of let's assume that like we have the y, right? The y is a perfect straight, but over time it can be like deformed like that. The deform the shape like that, either it might be because of the electro migration. I think I explained to you like previously. Over time, the electron will be like migrate outside. So I think it migrate the things like that, or even like during the manufacturing, the shape will be like this too. I remember. I think I already told you like because the reason for that is the reason for the deformation like that is the technology right now is about 3 nanometer, the newest one. The current one in the market that you guys get in the cell phone is a 4 nanometer. 4 nanometer, and then the photo optics equipment can only go down like it's, if you think about like the um, normally, like you remember like when they do the photo, right? The photo, they just apply the film, and then the light through the film and to the paper, right? The photo stop paper, and that one it will like change, and then you get your picture, you get the photo. With that, now you have the size of like 1-2 centimeter or like 3-4 centimeter. Now you have that like go down all the way like 2 nanometer, which is like let's see, about like 1 billion times smaller. So the most modern photo equipment can only handle down to I think about like 120 100 nanometer, or like about 90 or 80 nanometer, something like that, bigger than 50 nanometer. Then the Y we have like this, we have the Y like this is like 20 nanometer, but the resolution of the photo equipment is only like 50 to 100 nanometer. So how can they deal with that? So they have to do like a 3 mask. Actually, it will go from 2 to 3 and then 4. So for the one is like so they have to do like a multiple, so that is quite like to like adjust and correct by themselves. So because it's like just one this, another one, I think it will be like that. Whatever, I think that's, I'm not like into like how they do that, but they have to use the 4 mask to be able to adjust the one, like the shape of the one to be correct. Even with that, it still cannot like straight. When you like when it project through the film and the mask, you see the mask go to the silicon, it will be this or be like that. So there will be all kind of effect, failure, short, open, and so forth. So that's why I think this is the manual. It can like the short can be short to the ground, can be short to like the VDD, and yeah. So all kind of thing here is like is yeah, I think those things you can read that, because I think I will go to further, like the more important thing is about the Stuttgart model, but those things I think you can read, right? So you have a anomaly in the gate oxide, which is the gate oxide supposed to be like this, right? This one is here. So you have this one transistor like this. Here you have a gate oxide. Here you have the gate here. I think it's too big. Okay. So here's the gate. Here's the gate oxide. This one is not straight, right? This one, it might be like this because of the deposit never even. This one lets you have and plus here and plus here and so on. So everything, every parameter, this one gate oxide, like what this one is the length, and I think this like you have like this. So this one is this one, sorry. So this one is the width of transistor. Width, length, gate oxide, and then like you have the doping and plus here, whatever, everything's vary. Because they vary, and also that's contribute to the variation. But here we talk about the defect, which is like the anomaly of this gate oxide. It might sometimes like touch it. It's like this. So it just like cause the transistor like malfunction, wide width, and so on. So I think I just talked about that. I think I talked about that already before. Maybe I just remind you guys about that. Contamination due to foreign particle. This one is in the doping, right? It's like we have doping here, and you have it there here, and it is a contamination due to foreign particle. It means like the doping is with the charge, intentional charge, but the foreign particle, which is something like it's not the silicon plus, or like it's not the doping, like intentional doping, but something else, like in the atmosphere, and then during the manufacturing it get into, then it causes the problem. The etching residue, the shortage in wiring. Here we have the etching residue, and we have a bridge due to foreign. Okay, yeah, this is the foreign particle, because you have this two wire like that. The foreign particle can fall into the middle, and if it's big enough, it bridge and it causes a short. That's another thing. Wider width and thicker thickness. I think this one is like a thicker or thinner, yeah, and so on. And this connection in wiring, as I talked earlier on, right? Sorry. Have this connection. So basically, I think this is to maintain, like we have it come down to open and short to the VDD and ground. VDD is like at 1 and ground is 0. So how do they model that? So for example, here those things, yeah, you say a foreign particle can do that, and here you have okay, you can look at that. Here's the size. It's a 2 micron, which is like this picture is a very old days, just like to like demonstrate about like the, you see that this one is the, yeah, this one is the metal here. This is the metal going, and then you have that, and in between I think we're in the middle, and then in between I think this one maybe, yeah, this connection due to the electron migration. Now purpose of test to test the manufacturing defect. So in this picture, you can see that there's like a known defect, and a defect. Okay, this one, yeah, you have the tester program here. You have a, well, I think this is obvious to me. You have a one is known defect, shipment defect, fail. That's it. And we have the ppm, which is a part per million, which is 1 e minus 6. So the defect is a 10 to 100 ppm. It means like every 1 million you have a 10 or 100 parts fail. Usually, I think it depends on like initially when like it come out to a new process or new technology, the yield. This one they call it the yield. The yield will be called like a percentage. So defect is called like ppm. So if you have the yield like the yield is initially usually it's only sometimes it's only 20-30% or even 5-10% because of too many parameter, too many like variable at the beginning that they don't control, and then like they cannot like model correctly. Two things: cannot control. Second is they don't model that correctly. So as I said, they have to do that, go through that, and they take some pattern, some sample, they measure it, and they go back and remodel that. That process will like a turnover for like I think at least 10-20 times to like polish the model and also polish the control variable. So at the end, the yield will be like up to like 80-90%, and when it's mature, it can get to 90%. But the first time come out, usually I think what we expect maybe only 5-10%. Then I think that's okay. I think this one is not much to say. You can read that. Task cost is increasing year by year. There's a two like a man to maintain decide that the cost like increase. So I think it's a complexity, simple complexity increase, which is I think it requires like a more like a finer tester or like a more sophisticated tester, right? So that means the cost increase. The because complexity it means like technology is like more advanced, so it requires more advanced tester. The second one is because the technology scale, which is the circuit or like the chip getting even smaller. No, the feature getting smaller. Let's say you go from like a 5 nanometer to 4 nanometer, which means that you can like pack into the same size, right? Like 80 by like about 40% more than before. So that means that the number of transistors will be packed into the same size chip will be 40% higher, which means the tester need to work 40% more, right? You need to test 40% more transistor. That's one thing. So more complicated, like a more cell, more area. That's about like only about the area, and the complexity here has all kind of thing. Complexity means like you have a higher advanced technology, so it means like you cannot take the tester of a tester for the technology 10 nanometer to test the technology for like 5 nanometer, right? And then the frequency, more feature too, more feature, because look, you have the same size, but now the number of transistor, when the scale is 80%, right? You scale down 80%, which means like the number of transistor will be increased by like 40%, right? So with that extra number of transistor, either they have to add feature in that, right? So they have to add feature in that. If they don't, then that means like they just okay. Let's say like you have the technology 5 nanometer is the size of 1 square millimeter. It has the feature 1. Now you take that 1 square millimeter, you migrate that into new technology of 4 nanometer. It will be scaled down to only like 0.64 square millimeter, right? Because 80% is the size is 0.64. But usually, then what do you do with the other like 0.36 square millimeter? It's waste. So usually, because of that, they will have two choices. One, either they will like reduce the area because the design is the same, but never that happen because 1 year later they will have a new idea. 1 year later they will have a more demand. They will have a, oh, okay, now demand is doing this. Oh, okay, well, I want that to do like better. I want that to have a more like feature. For example, you look at the cell phone. Cell phone is the very like a lively example for the advance and progress of technology. Every cell phone come out the next year, there will be new feature every year. That's because the chip provided in the cell phone is also like advanced. It's also like progress, right? So which is I think at the end of the day you have that like everything that come out like more complicated and so on. So the cost must be like even more. So it's no surprise. There's two things: complexity, and this one is just a purely like a area or like a number of transistor. Manufacturing cost is going down. That I think is oh no. Oh, cost per transistor. That's right. Cost per transistor going down for sure because you have now is the number of transistor increase. So that's why you have this one going down. Because in the 1 square millimeter now you have a more transistor than before, right? And then like usually the vendor will sell the chip basically in terms of silicon area. So for example, of the same kind of chip, let's say the CPU from Intel, if it like have the CPU of like 100 square millimeter and another one is like 50 square millimeter, so the price between the two is roughly like half of the other one. It's kind of proportional to the area. So which is that you have that now if the size, right, the size stays the same and you have a more transistor, it means that the cost per transistor will be like going down. Yeah, remember I think the first IC come out for the CPU for the Intel is 4004. There's only like a couple thousand transistor, and okay, it's crazy. Just a little bit history for you guys. At the time, the cost of that, the price of the 4001, the first one come out is in the $1,000, and then only like I think couple thousand or 10,000 transistors something. So you can see that one transistor costs about like a 10 cent to $1, and now you have a chip. You have a chip, a billion transistor is cost like maybe $100. So it's really like almost nothing. But you have billion, so it's still something like $100. Now let's see like where the DFT fit in. So what you know that the DFT, we see like what is the definition correctly, precisely for the DFT. But the DFT flow, like the design forecast, it will be included during the layout design. I will explain that later. But the picture here means like DFT right after the logic design and before the layout design. This one won't work. I will explain that later. Okay, so it's like after the logic synthesis, then we will have the layout design. But the layout design here we have like a placement. Then we have a CTS placement, CTS round and post round. Basically post round. Basically the DFT will go in here after placement. Why? Okay, I will explain later. Impact of the SoC design trend. This one is, I think, this one is for. We have an L bit, and then we have an M bit, right? L bit is a logic. BIST is a built-in self-test. So that means that the design for test is, I think, two part of that. One is you insert the logic, so that into the design, so that part of logic will like will check, will help, actually will not really, will help check the defect inside the chip. But it's like a cell test, which is it can test. That means that you still need a tester outside, but the tester outside like cannot like go inside the chip, right? Let's say the chip like a billion transistor, so how can like okay, simply you remember when you want to measure, you want to test something, you have to measure it, right? You have to be able to probe it. So you have the probe, you poke into like the node, and then you measure the voltage, or you measure something, and then you probe it, and you know if it works or not. And now with the design, it has a billion transistor. I think how can we like poke the probe, like poke that inside into like the internal of the chip to measure it? There's no way. So that's why we have to insert the logic in there, and that logic inside the circuit, those logic will take care of the situation, will check the situation or status to find out the defect, and then it will like send out a signal outside, and that the tester will be like able to read those signal outside at the external to know that if the design is has a failure or not. So one is the part test the logic is called like a L bits. The part test the memory will call like a M bits, which is a memory, and then frequency usually usually around like 20-30 megahertz, and maximum there's also some like maximum like 100 megahertz. So but the higher frequency, the costly tester. So usually I think it's the 20-30 megahertz, that's the most popular now. 30%, okay. Test time increase. Yeah, you see that? I think in this picture you have a logic or like whatever here. 30% increase a year, test time increase proportionally to size. So it is a proportional to size, and also not even it's the same size, but now it's still like the test time because of the advance, right? The advanced technology that I think it does contribute to the cost. So test time increase because of the size, and the cost also. Time is money. More time, more money. More advanced, more money. High speed, more money. Everything costs. Now it's just like the test we talk about to discover the failure inside the chip is called structural test, and then it will cover the faults by modeling the faults. So you can see like on the left is like functional test. Functional test is like for the stuck at fault, right? This one is difficult to check for the functional test. Imagine, okay, you can imagine something like this. Functional test is kind of like the test with the black box. So with the black box, you can know much inside what it is. So how can we check what is a failure inside the chip? So that's why I think there's a really like for the lab here, basically it's not fit for the failure discovery. So that means like we have to go with that. So to discover the fault, we have to see the fault, or we have to model the faults, right? So that's why I think that then that's why I mean. But first of all, it's this definition is a simple one. Fault coverage, it means like you have a total like detected. You can detect how many, and in a total. Usually, I think the total you cannot know either. Actually, how can you know how many phones in a circuit, right? You can know only the phones you discover, but the total number of phones in the circuit, actually, there's some like a statistic for that, so they can like they can derive for that. I don't know how they derive that, but usually they can like calculate that, and they have like, oh, here I have like we can discover that much, and then like with this with this for model, we can discover that many. So they can give us a number like the phone coverage of 90 or to 95%. That's like still that's a theoretically, because really in real life, or like in real total number of phones in the circuit, how can we know? So it's just like some number that like in theory they calculate that, and then they has a theory to do that. So basically is like that. Now we have like a Stuttgart form, right, model. Before we go to this one, I think I need to explain what is a Stuttgart form model first. So I think we go to this one. Yeah, here. Ah. Okay. Yeah. Stuttgart form. What is it? It's a simple like when, let's say you have this one is the table for the inverter, right? The inverter, so you have so it can happen, we have a one input and one output. The failure, the defect can happen at the input or at the output, right? And at the input, it can be like it can be short to 0 or short to 1. So when it's a short to 0, like to ground, it called that like stuck at 0. When it's short to VDD, it called like stuck at 1, right? So that means we have a like the input A short at 1, or like stuck at 1, stuck at 0. The same thing. Output is D. The D is a short at 1 or short at 0. So in the case like for the output, sure, I think it's like by itself it cannot be like you cannot force the output. You have to force the inputs to have the output value. But in real life, the output can be short too. So if it's short at 1 or 0, how to expose it? So let's say like how to expose it. It means like if it's short at 0, right? You have there's a two conditions to expose it. The condition, the first one is if it's short at 0, we have to apply the value of that input to the opposite value, so that like it can get out, right? It can like we can see it. Let's say if it's short at 0, we apply the vector at 0, doesn't mean anything because it's the same as the stuck as the short one, so it doesn't make any sense. But if it's short at 0, if we want to check it, if that input or like that node is a short at 0, we have to apply the input vector so that that node will have the opposite value of the stuck at value we want to check. That means that the first condition is you have to apply the vector such that the like goes to like the opposite value of the stuck at check. Which is like if we want to say like stuck at 1, then we have to apply whatever so that we have the value is at 0, and vice versa. The second is we have to apply the vector such that it will allow the bit. So it will allow the bit we check to pass through to the output, right? Because if we have a vector applied and then that bit, this bit cannot go out to the output, so what can we measure, right? We can only know that value is correct or not by measure at the output. If we cannot measure it, then the vector, that's not the vector we want. For example, here you see that, let's say like this one, I take a example here. The input A, if it's stuck at 1, right? It's stuck at 1, then we have to like apply the input 0. right? We apply the input 0. If it pass, it means we have an output 1, which is correct. But if like the input A is stuck at 1, then it will get this value, right? That's why failed in D. Pass is this. The same thing if like you have like to check if the input is stuck at 0, we have to up to, in this case it is a simple, so we just apply the opposite value because only the input A. In the more complicated circuit with the node inside, like an intermediate node, we have to like apply the vector at the input so that that intermediate node will get the value we want, right? So now I think the other one. Now let's say like go to the output. So the output here is like if stuck at 1, right? So then we have to apply the input vector so that the output will have the opposite value, right? So that this one is opposite value. For the output to have 0, we have to apply the input A, right? It has a value 1. So if we apply the value 1 and we got 0, it means that like this one is good. But if we got the value 1, we know that like the output stuck at 1. And vice versa, we have that one the same thing. To check if the output stuck at 0, we have to apply a vector so that the value of the D here has an opposite value, which is a 1. So to have an output at 1, we have to apply the input vector is a 0. So if we apply the input value is 0 and we got the output still 0, we know that like this didn't fail. That's how we can expose that. So that's like a unit. In this case, you don't see the like this is condition 1 and the condition 2. You don't see the condition 2 apply here because we have only like the simple inverter, right? So you apply, go out. It doesn't need to be like anything. So we don't need to have the vector that satisfy the condition to allow the bit to propagate like to go to the output. So now if you can see that we have that means like to discover 4 cases, right? 4 cases. One is input A stuck at 1, stuck at 0, output stuck at 1, stuck at 0, right? We have to do 4 times. However, you can see that the input vector is only 0 and 1. So when I apply 0, it will allow me to discover the stuck at input A stuck at 1 and output D stuck at 0, right? 1, I have that like sorry, here 0, it will allow me to detect the input A stuck at 1 and this. And if I apply the vector input as 1, I have 2 cases, which is even I have 4 stuck at to check, but I need only 2 vectors. So that's called form collapsing. But here is the inverter. Now we go to this is the NAND gate. The NAND gate, the same thing. We have let's say like a, you will see that like how the condition 2 will be applied, which is we have to apply a vector so that the bit we want to check can pass to the output, which in this case, if we want to check the A input stuck at 1, right? We want to check this one. Let's start with this one. So we want to check that like first of all, the input B need to let the here's the A and B, right? And the output here is a Y. So now we check A, right? We check this one. We check that like we test that if it's stuck at 1. But first of all, we need this input, this signal need to go out. If I apply B is 0 here, then no matter what A is, no matter what A is 0 or 1, I always have the output 1. So it means that the vector I apply whatever like let's say like A and B, So the vector AB. Okay. Then if I have AB like this, so that means like whatever for that, if B equal to 0, right? So X, that means like no valid vector, right? No valid vector. Because when I have 0 here, the A cannot go out. A cannot go out, which means that doesn't work. That's why like when you have that, you have B. When you text, look at that. When you text A stuck at 1 or 0, the vector B need to be 1 here. Because if it is 1, right? It's 1 here. Now the A can go out. Then we can check, right? So now we take 1 here, and then if we take a stuck at 1, that means that we have to apply the value, opposite value is 0, right? 0, then we have the 0 here, we go through here, become 1. So if the 1 is correct and 4 is 0. Like similarly, if you take 0 here, then you have to opposite value that 1, and then and so on. You take the same thing, look at that for B too. You can say B, for that, for like a B to check, it need to set like the A 1, right? Now you check B, right? Now you check B, it means you have to set here 1, so that the value from B can go through, right? So vice versa. Now that's like we take the input. Now if we test the, let's say we test the output stuck at 1. Output stuck at 1, for the output to be 1, right? For the output to be 1, so we have like the input need to be, either input need to be 0, right? So you have that, but it's here, I think it is stuck at 1, they need to have a 1 of the two is a 0. Okay, and then because okay, stuck at 1, it means that we need to apply, let me clean it up. So I clean that, right? Okay, good. Now I want to check like if it's stuck at 1. Stuck at 1. Remember, if I want to check the Y, the output Y stuck at 1, I need to apply, like I need to have to expose this one to 0, right? For that to be 0, so which means like both the input here need to be 1, right? For that output 0, you have to have AB is equal to 1, so which is the vector you apply here is 1 and 1. The same thing. Now you want to check like if Y is a S, like Y is a 0, so you have two cases. For that to be 0 here, then you have now stuck at 0, right? Then you need to apply like the input value so that Y will become 1, like opposite of the stuck value. So Y become 1 when either A or B is a 0. That's why you have two cases, like B equal to 0 or this one equal to 0. Right, and the other one is like this case too, but this one is covered by the other one. So that's why I think you have all like this one is the table, the stuck form list. So the stuck form list you have okay. So now the coverage. The coverage here you have the combination of the input A and B. You have a 4 combination, right? 1 0 1 1 0 0 1 0 1. However, we don't need 4 combination, 4 vector. That means that when 4 combination, or like here we have a total 4 vector, but we need only 3. The reason is that you can see that when it's a 0 0 like this one, right? Vector here, it is cover. It cover what? It cover the 1 0 0. It cover the Y stuck at 0, right? Y stuck at 0, but Y stuck at 0 here, it is covered by this one too, right? And it's covered by both. So because it's covered by these two things, then I think this one we don't need to include into the vector anymore. So we need only 3 vector. That's called like that means like we list all the vector and we just reduce that, similar to the way that when we optimize the Cogno card, right? You remember like in the digital technique, we have that like how to optimize the Boolean function. This one is not the same, but it's kind of similar. So you just like reduce that. So with that, I think we go back to the picture from, I think, the other one. So now with this one, first of all, I think they will like the easiest one is to first one it's a stuck, not stack. Okay, it's STUCK, stuck, which means stuck, uh, glued to or cling to or whatever, stuck, not stack. Okay, in this picture, we have a tree that this circuit has a three input S1, S2, and X3, and the output is Y. And the way they model that is they will model every input of the cell will be designated like a variable. You can see that even we have X1, but we still have A, B, and C, right? And then like a B here, and we have a D and Y. So it just for like clarity. We might not need that. We might like if we do that, we can like whatever we do that but for the purpose of clarity and then for the check inside, I think they will do that. Now I think let's say like they check first, check the output, which is you have the node Y, right? So first of all, x1, x2, x3, and y here. This one is like the function, the correct function, correct operation of circuit. So it's supposed to be like when you have a three variable, which is you have a combination, right? A combination from here to here, and accordingly you have the value of the output will be 0, 1, 0, 0, 0, 1, 1, 1. So one fast look is that you have the y here, you have the a like x1 and x3 is going to dominate the two end here, right? If a x1 is or a, if a is a 0, then it pass like it block this NAND gate on the left. If C is a 0, it block the thing here. So if those things go out here, 0, 0 here, you have a 0 at the output. So that means like if you can see that 0 like a bit 0, 0, 0, 0, 0. When you have the MSB and LSB 0, 0, you have a 0 here, right? So you have two cases here, and yeah, that's it. Okay, that's just like a quick note. Now we have to go to the output I. Output I, like now, I think if it's stuck at 0, which means you have all the way 0 here, and you have all the way 1 here when it's stuck at 1. That's fine. Now the way that like it's color gray here, it means that this one is a cover. So this vector, which means like the vector 0, 0, 1, cover the fault of the I stuck at 0. So it's color that. So 0, 0 will cover the font as stuck at 1 with the output 1. So let's see like how it works, right? So this one, let's say like you have the output. The output, let's say like to test the output I, if it's stuck at 0 or not, right? This one is stuck at 0. So we have, because we want that to be 0 here, then we have to apply the value of like so that we have a one of the two here is 1, right? But this vector, this vector here, okay, let's I think do in backward. Now we have a vector 0, 0. Does it expose the stuck at 0? If I have 0, 0, 0 here, that means I have a 0 here, 0 here, and 0 here. As I said at the beginning, if I have 0 here, it go through here. This one is 17. I have a 0 here and 0 here. So that means the output will be always 0. If the output is 0, is the same as the value we want to check. We want to check it as stuck at 0 or not, and the output is 0 regardless of like it's stuck or not, right? At 0 or not. So that means that this vector cannot expose the stuck at 0 for the output. Now with the 1, right? With the stuck at 1, it does, because now if you apply 0, 0, 0, the output will be 0. If the output is like to 1, there's a difference. So which is that's why like the vector 0, 0 expose the stuck at 1 of the I output or of the node I. So that's why it's here is gray. Let's check this one, and then all the other one you can like similarly like derive from there. Now this vector 0, 0, 1. Now let me like restart with the 0, 0, 1. Right, so we have a 0, 0, 1. So 0 here, go down the way here, you have a 0 here, right? 1 here, you have 1 here. Now 0 here, go down here, you have 1 here. 1, 1 here, you have a 1 here. So 0, 1, then output you will have 1, right? Output is 1. So with the vector 0, 0, 1, you have the output 1. So the output 1 is like you have the value output 1 is opposite of the stuck at 0 we want to check here. Then it exposed, right? When you apply the vector input vector 0, 0, 1, you expect the output will be 1. But because the output is like the I here stuck at 0, so that means that this vector expose the stuck at 0 for the node I. The same thing you do like this one. Just apply 0, 1, 0, right? Now, let me do one more time. Now the vector now is 0, 1, 0. The vector is 0, 1, 0. So 0, 1, 0. 0, 1, 0, right? So the output is because it's 0, 1, 0. So you have here 0, 0, and the output will be 0, right? So it will happen the same thing like for the first, for this one. Because it had the output like 0. So because the output is 0, it's the same value as a stuck at 0. So it cannot expose that stuck. So it can only expose the stuck at 1 because 0, right? The output supposed to be 0 is different from the value like a stuck at 1 here. And so on. You just like test the thing, and then you can see that like all the like you see gray is like where it covered the fault. With that, I think we know the next one we have this one. I think that's just like intermediate thing. So this now you go like instead of going like horizontal, now you go vertical. The same thing you will see that like the same thing you will explore like a reason derived similar to before. So let me take this case. Why this one like expose the fault and this 0 is not, right? So let me check first of all like the vector 0, 0, 0 again 0, 0, 0. Now you have a C input, which is this one, right? So it's stuck at 1. But first of all I think okay, this one is a simple 0, 0, which means you apply for C value 0. If stuck at 1, 0 is the opposite of 1, right? That means that's how it will expose. But now we see like if the vector 0, 0 allow this bit to go all the way through, right? There's a two conditions. Remember, one is you apply the bit value so that it's opposite to stuck at. Here it's like here's a stuck at 1, right? Stuck at 1 for C. Stuck at 1 for C. So you have to apply the bit for C is a 0, which is here. 0 is here for the C. That's qualify for the first criteria. Now the second criteria is we need to apply the bit like A and B so that this one go through and then expose at the output, because here that's how like we measure at the output here. So for this one to go past, we need this one to be 0, right? Or this one to be 0. So that like this one, because if this one is a 1, then doesn't matter how much this one is. What is the value of this one? This one will always be 1, right? It's an OR gate. So which is we need the value here is to be 0. we need the value for this one to be 0. That means we need this one, either this one 0 or this one 0, right? Either, not both, but both is correct too. So like at least one of the two. So that means that the vector to check this one, to check this SA1 will be, will be first, if I say A, B, and C. C will be like 0. And the value for the B and C, that means I need this one like A and B, actually A and B. So A and B will be 0, 1, 0, 1, 0, and 0, 0. And one, yeah, one of that should. There. So that means that the three vector to cover that, let's see this one, it will be 0, 1, 0, 1, 0, 0, 0, 0, 0, which is, it will be this. You have a 0, 0, this one. Yeah, 1, 0, 0 will be this one. And then 0, 1, 0 will be this one. So you see that here. See this and this. What's it? 0, 0, 0. I think this one. Oh, okay. I think there's a, okay. I think there's a, okay, let me go back, because there's a, because if this one, if we have this one is 1. Now this one, actually, if this one is a 0, actually, this one will come out here as a 1. I need two things. One, this one go through, which is I think this one go through, and then this one is a 1 too. So this one need to be 1 here, right? Because it's a 0, then this bit C cannot go out. So you have a 1 here, which is this bit need to be 0 too. So which is we don't have this, the bit B cannot be 1. So this one is wrong. So there's a two vector 1, 0, 0 and 0, 0, 0 to allow like to check the stuck at 1 for the bit C, which is here. Yeah, two things. Here's 0, 0, 0 and which is here, and 1, 0, 0. Yep, that's a 0, 0, 0 and 1, 0, 0. So you see that? That's two things. So with that, right? So we can like you can do that, and then you can like, let me I think this one they do this, but I think let me do the same thing. Maybe do horizontal is better than the vertical. Now let me check like the okay, let me check this one, G, right? G. So we have 1, 2, 3, 4 coverage, right? So we check like SA1. Let's check like a G stuck at 1. For this one stuck at 1, we need this one to be 0, right? We need to apply that like stuck at 1. We need to apply so that the G node will have the value 0. That's first thing. And we want for this G to go out, we have to have this value here need to be 0 too, so that like this one can go out, because the H, if it's 1, then it block the signal G come out. So we need that to be 0. The H to be the H, when okay, for H to be 0, then I think either this one 0 or this one 0, right? So this one, so that means a 0. And for this the F to be 0, then we have this one is 1. So this one, and then for this G, for this, and then the other one, we have the G, for G to be 0. So either one here, you have a 0 here or 0 here, right? Or, but because you can see that for the pass go out, we have this one need to be 1 already. So this one can only be 1 here. So that means like X1 or A need to be 0. So from here, we can like have A, B, C. So it's a 3 vector, and then we have we can see that we can write it down, right? So we need A to be 0, so we have a 0 here, right? And then B can be what? Yeah, 0. this one is be 1, and then C can be 0, or like can be 1 too, because here you have a F, right? F can be 0 or C can be 0. So that means that when F is a 0, which is you have a B is a 0. Oh, hold on. Sorry. I think, okay, just like follow the logic as I explained. I think we will have like the thing go like we have 4 cases here. This I know that like it's a little bit confusing to you guys. So I think at the end of the day you can ask, or like you can ask next time. But I think you can like you can quite derive from there, right? It's a little bit confusing, but I think you can figure it out. Because to me, it's not like I do that like right at the first time. So it needs a little bit of reasoning. Now we come to like the same thing, reduce the number of test vector, right? So the number of test vector when we have like here we have a vector, but we need only 4 vector because it cover everything. You can see that because if we look at this one vector, this vector, right? This vector, let's say this one. So this vector is covered by this one. You see that this one cover in here. This one covered by this one, right? This one is same as this, and this. So because this vector 0, 0 is covered by vector 1, 0, 0, then we just like don't need this one. We just skip this one, right? Now the second one is you can see that 0, 1, 0 here, 0, 1, 0 here is covered by the 0, 1, 1. See? 0, 1, 0 is covered by this. This one go here, same thing. Then we just remove this one. The same thing, I think vector here, this vector, you can see that is this one is covered by the, I think on the left. This 101 is covered by this one, right? Here, 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 and here, and here. It's the same. So which is, I just remove it, right? So I remove it, so 3. Now the last one, you see that? The last one is the same as this one is the same as this one. Finally, I have only like a 4 vector left. So to test all the stuck like model here, I just need like a 4 vector. This one is like the collapse thing. So now, until now, they will give you like the real definition of DFT. So the DFT is a design technique that adds the test circuits inside the LSI hardware. So these added circuits permit to easily apply tests on the design LSI after manufacturing. Let me explain that like in like plain English, which is you have a bunch of things in here, right? Your circuits in here is your input. You have a 10K input, you have a 1K output, go out. So how can you detect the failure at this node or this node? How? If from outside the tester here, it applied the vector here, then it read in this one here. How can they know that this thing here? If there's no way to like to check if like you have this here, right? And you have this here, and so on. How can like like this node or this node or this node like stuck at 0 or like a short to 1 or short to 0? There's no way to do that. Except that you have to insert your circuit here. You insert like some like logic here. It poke into that. And then this circuit, it read this in, and they go out here. So which is like now this is your input vector you put into here, and this one I think will intervene, like will read the status of a certain like point, a certain location in the circuit, and then after it read all the thing, it will give the signal here, and the tester, here's a tester, the ATE, which is automatic test equipment. So you read that, then now we know that like, oh, this location has a failure. So which is, that's like the DFT is there's two part of that. You have actually there's a three part. The first part is the test circuit. The second is actually this one is the same. This one is the circuit to insert into the, so this one is a test circuit, the additional circuit, the flow insert into the design. The second is that we have to like have the vector, the text vector, as we just talked previously, right? This one is text vector. We have to prepare that. So that text vector, basically it is like a simple because you have only like the 3 input circuit. But imagine you have a 10K of that, you have like a 2 power 10K. I don't know what is the number calculate. I think it's maybe like a B trillion or something. But they said that with that it can take like around like a century to calculate that. So we cannot do it. So that's why they have the design, like they insert that, they do this way, they check, and then like they read the back here. That's how the design for text, that's all these three things. Insert this one, create, listen that this one is one thing, two things. Create the circuit and then insert that, call that one. So you create and you insert here, and second, you will like create, like generate the vector, the text vector, so that you can like read the status inside the the design, and you read that and you know like where's the failure, right? So now I think the target of DFT is to minimize area overhead, which means like this is a circuit, right? This is a circuit. When you insert that, you have to insert like you should not, let's say like your design is a 1 billion transistor. You cannot insert another 1 billion transistor to read those things, right? It's not one to one. Or you don't even insert like a million transistor to read those things. So there's a goal for the DFT to create like the minimum area that can execute like the function of test, like a test the circuit inside. And then the second thing is increase the test of phone coverage. The phone coverage here is what we talked about. They calculate that. To be honest, I don't know how they calculate. I have some like format. I calculate that to see how much like a coverage. I think the guys said only like that one is calculated by the flow. So they calculate is, oh, with this we have a 10 like a 90% coverage. Usually I think 90 to 95% cover, and then we good. And then it need to satisfy the phone coverage, because you insert the circuit here, but it cover only 50% of the phone coverage. Then that's a failure, because the other 50% will fail that you don't know, right? And minimize the test time and minimize the test cost. Minimize test time, it means also like minimize the cost. But when you minimize the time, remember time is money, but you minimize the time, which is the speed. It means that you have to increase the area, which is you increase the money. Area equivalent to money. More silicon, more money. More time, more money. But the time, okay. So which is I think we have to like minimize the test time. Let's say like the test time, if it has to go like if a chip go through the tester take 1 second, and another chip go through it take only like a half second. It means like the chip go through with half second will have less cost, right? It's obvious. Require quality and test level. I think those things I think you can figure it out. This is oh, okay, there's another thing here. Test condition, which is this one is the operating condition. We have a temperature, voltage, frequency, time, etc. This thing is like when we fit the chip into the tester, it will have a different because the chip supposed to work at that. That's like a PVT. Here's a process is a transistor process. V here is voltage, and here's the temperature. So this one is a T process. It means like we have to force the which is, I think, if you read the SD18, it will have a width typical strong. That's about transistor. That's transistor here, XTOR. So the transistor can be weak, typical, and strong, right? Strong when it's like run the fastest, because you see here's a distribution of the current go through the of the transistor. There's a like a here's the strong. If I have this here, right? This one is a distribution. This one is a current. So if you have the current, like big current, that would mean like a strong, because strong means like it runs fast. If this one is like weak, and this one is a typical. So if you have then I think this typical, weak, typical, strong. That's the process. So when you test this one, you have to assume like the transistor, like some is strong, some is weak, and some is typical. That's the thing. And the voltage, because you have the voltage, you have to apply the voltage is like you have the regulator, right? Voltage regulator apply like connected to the VDD of the chip, because it say that like a voltage regulator, but it can like fluctuate anyway. So the standard let's say the standard voltage is 1 volt, but it can be never ever like a 1 volt all the time. It will fluctuate between, let's say, like 5%, which is like 0.95 to 105, right? So 1 is a typical, and 0.95 is the weak, and 1.05 is the strong. So with that, when we do the test, we have to apply the voltage 0.95 and also 105, because that's at the extreme boundary that the chip can fail. Not only like they detect the failure because of the failure inside the chip, but it's also like because of the test condition too, or like the um, the condition at which the circuit operates, right? So and the another one is that you have voltage and then you have temperature. Let's say you put your chip like in the air conditioning, like air conditioned room, then you have the temperature is in the 25 degree or 20 degrees C, so it works perfectly. But that chip, if now you bring to like a Siberia, so it can go down to like a minus 50 C, so the transistor will work completely different, and the resistance will be completely, and we have to make sure that it's still working. And when you go to the desert, right, like a Sahara or something, it's very hot. So and then the tester will have those kind. It will apply the condition like 0.95, and then the temperature will be like a minus 40, and here it's like a minus 155. That's the standard. Minus 155 C and minus 40 C, minus 55 C too. This condition are the extreme conditions, so that they test the chip if the chip still working. Those thing is like a reliability target. The target knows, I think usually, you see, it depends on the demand, like the requirement of the end circuit, the end product. For the automobile, like for the car, right? It need 20 years. Why? Because the car need to last long as like at least 20 years. Nobody like buy a car for like and then after 10 years, 5 years it broke down, right? So if the car can run for like 20 years, then the part need to be able like to last for 20 years too. And the car electronic is 10 years. This means like this car electronic like some kind of like infotainment, some not like life and death, not really like for example, you have in the car there's an ABS system. The ABS system, it means ABS, automatic brake system. In that there will be ABS, automatic like a brake sensor. There will be sensor in there to sense the if we hit the brake or not. So this one need to be like completely very working all the time, because if not, when you like break the car, it need to stop slowly, not slowly but gradually, because before we have the ABS, when you hit the brake, the car, when you run at the high speed, the car will spin around, and that causes a lot of accident. So when the ABS come out, and it will like to be brief, it will help the driver like control the speed. So when you hit that, you brake, then the car like no longer like spin around. So because of it, the ABS need to work like the reliability is very high. It need to be 20 years, or it tests in very very harsh condition, like high temperature, low voltage, and so on. And then it need to test like there's a good question. I think there's a good thing, and if you notice, how can they test that? How can they test that like the part will last for 20 years? They don't like give the part like and test that 20 years before they give that to the car, right? Because if it takes 20 years, then the part will become like, okay, it costs too much. So the way like how they do that, so there's a very good way to do that. They just do a process is called burn in. That's the process to do it. Burn in. So they just like accelerate the the time, the aging, which is like okay, they know that at 20 years with that condition, now they just push like the temperature, they push like they push the temperature higher, a certain level higher, and they push something like the process, they push, they have the burning, which is they make the condition even harsher. That means even more difficult to be equivalent to like the 20 years. So that means they will test for maybe like 1 or 2 minutes, 1 or 2 minutes, or like 10 minutes. That 10 minutes of burning condition will be equivalent to like a 20 years. So that is like a kind of like in the factory. All right. So the same thing for 10 years or whatever. That's how it works. Then now I think we have 10 years, and then like 10 years is for the thing in the car, like the infotainment, right? Infotainment, like for the music, for the things, whatever the things are. So it still need to work after 10 years, right? So in yeah, it doesn't need to be like 20 years, but after 10 years, that's okay. And you have to like find like buy a new one, replace the music thing, like the equipment, but they don't guarantee, because the more time they have to guarantee, it will be the more money. I need to take a break here, and then go back at 9 or 9, 10, 19. Okay, anyway, we take a break. And in the meantime, I think you guys can check. Yeah, go back to the StatCAD. I think that's not. I think that's not difficult. It's just a little bit confusing.
Alo. Các bạn nhắc lại ha, tức là tuần sau chúng ta nghỉ 30 tháng 4, cho nên là các bạn tham gia vào cái lớp ngày thứ năm nha, sáng thứ năm 8 giờ trùng với lớp CC01. Tôi đã gửi tin nhắn ở đây và gửi trên hệ thống BK e-learning rồi đó. Hai bạn nào không tham gia học hôm nay thì có thể nhận tin nhắn trên BK e-learning. Còn các bạn ở đây thì tôi đã nhắc đầu lớp là đầu giờ đã nhắc, bây giờ nhắc và gửi tin nhắn luôn nha, các bạn chú ý nha.
Okay, let's get back. Okay, now I think let's say like in the real circuit, it would be like the circuit we mentioned previously is like we have the 3 input, right, and 1 output, and that 3 input you can take it is a 3 input come from the 3 flip flop here. You see me? You see that? Oh yeah, here. Yeah, okay, you see my the mouse. So the mouse here, so that means that this input will be 3 input here, right? And the output will be like at the input of the flop, D flop. So if you take at that, so I think now I think it become like this the example like I presented previously will be like similar to this. In this case, it's not the same, but it's kind of like conceptual, right? So we have that here. Then we have the same thing. It will be like we apply the thing, the same thing. We apply the thing, and we get the vector, and we have a vector A, B, C, D, E, F, G, H, like the A combination. But we need only in this case. You see that it needs 6 vector instead of 4 in this case. So that's why I think we have that. I think the same thing. We know the net list, then we do that. We have so we figure out like what is the vector to apply to like f1, f2, f2, f3. So just take it as a similar. You can derive it. Now, how can we get the value out, right? So that means like this one is going in, it's out. So we need to read. We need to be able to read this value out, so that we can check. We have the vector apply here, right? So then we have to read that out so that we know that like it's stuck at here or it's stuck at here or it's stuck at here, whatever. The thing is, then they have the mux scan. They introduce the new flop, which is they will use the mux scan. The mux scan is a simple. The mux scan is this. Let me first of all, I think I have to. The mux scan. Okay, here's the regular flop. The mux scan is they introduce the mux at the input of the D. And one input is the regular data, the other input is scanning. And we have the scan enable, right? When the scan enable is 1, the input to the D is the scanning. When it's a 0, the input is data. So when it's a 0, it means that the circuit operates as a normal. But when this input, this scan enable is a 1, then like now it's only scanning. So what is the scanning means? Which is you see that you have a scanning port here. So if this is a flip flop is a mux scan, then it will go in, go out, and go right to the next one. So it will go like this. That's why you see that it's become like scan and chain. It's chain, scan chain. Those scan like form the scan chain. So you see that you go. That means let's say like I fit the bit 1 here. Then let's see. You have how many input here? One. How many flip flop? That means how many input? Because each flip flop you have that. Not really. Sorry. Take it back. How many for each like that? We have a 3 here. You go to this here. So that means you have a 3 input here, and this one similar, and you have that. So the number of input, that means like each time you fit in here, instead of fit in like in parallel, you fit it in as a series. So the vector will be fit into the data the circuit in series, not in parallel, right? It's the same thing as the 8251 chip. So the series data. When you fit the data in here, it will go like go this way. It go this, it go out, and the scan out here will go to the next flop with the scanning of the next flop like this. Go in, and then output here. It go to next stage. It just keep going, and at the end, it go to the scan out port. It's here that we will read the data. So how you see that because we have that, right? So we have this one. So we check that the now that's all. Now I explain why the DFT need to be done after the placement but not before the placement. So you see that the scan chain, here is really scan chain, right? Is a chain here. If before the placement we don't know this is a flop where they are placed, so which is this one we don't know, then we cannot connect like we don't know if we connect the output of this flop to this input or we connect this one to this one. Let's say because we don't know where the flops are, then we might connect this one, and then this one go back here, and this one outside go back here, and this one go back here. and this one go here. It's kind of messed up, right? So which is what is the consequence of that? When you have like let's say this flop here and this flop here, that far away. So you have to go from here until here. So you can see that when it's a far away, you have a more wide. That means a more delay. That means like it kill the performance. Which is, and the second thing is because the more wide is used by those things, it will mess up the routing of the design. You have a thousand of, not thousand, 10,000 of no, you have not 10,000. You have 100,000 of flop in the design. If you take like this, you have the things go like all over the circuit. You can imagine that, right? You have the connection all over the place, and it causes like now it becomes like chaotic. Because of it, we can only like insert the DFT after placement. Now we know like oh, here you see that this flop stay here, stay here, stay here, and so on, right? So that the DFT know where the place where the flops are placed, then we'll insert the and we'll like connect the second chain. You connect this, you go like this, so that like the length will be minimized. So that like a one main reason that we need. There's also other reason, but it's just like it will be more complicated. So I think it's just like mention one reason that the location of the flop. Now you can see that. Now you see that they will apply, and you have a vector 101, right? This one will be like this vector, and they will this the test pattern. Then when they fit into, it will go through, and they will read out. When they read out, the tester will read the data out. They will read it, they will fit in, and they go through all the thing, and they will read out. They expect to read the same pattern, right? Compare with the standard pattern, and we see like if it read out like instead of 101, is there like 100, they know that this one has a problem. Then I think yes, scan out this thing is just now test point insertion TPI. When you have like between here, right? If you have only like the simple circuit like we described here, so there's nothing to talk about. But when it is like you have here in between, you have like 1,000, like 10,000 of gates in between. So the thing is complicated that like it's really like difficult to figure out where's the problem. So they will insert like in the middle. They call that like to observe, right? So instead of they insert some flop in the middle to like observe the point, right? It's just put it here, and then this one is like will be into you have a get in here. It's just like in the middle, so that like it's just additional flop to instead of mux scan. This one additional is called like TPI. Now it's a design flow, right? So I think we talk about the design. DFT design will be the DFT insertion, scan insertion. That's what we talk about. It will be in the middle of the layout here. The middle of layout here, as I talked previously. So the second thing is ATPG, which is like a will is automatic test pattern generation. So it will generate the pattern. So you see that only three, right? We have the previously I described only the three input circuit, and then we have to figure out the vector and so on. Those things we cannot do that manually. So it need to like have a generator, which is a software to generate that for us. The generator, the software will read the netlist and figure out what pattern to like what vectors to cover the stuck at 10 at whatever like inside, and then they will have the target of 90 to 95%, so that like because they cannot cover 100% because they don't know even like what 100% really 100%, that means like everything will be in like into the table, so it's impossible. I think it's yeah, I think this quite this one is the design rule check. This, yeah, I think this nothing much to say. Yeah, design rule checker. So in the DFT, there will be like we need to define some rule for the DFT. That's why they just check the design rule for the DFT. Okay, those things I think those things is don't need to make it simple. It's not. Now it's a compress. So the data, you can see that the scan, right? The scan data, when you have a, let me see, no, this one is not clear. Let me show you another one. This, I will show you like the, not this one, so yeah, this one. Okay. It's a test compression, right? So the thing is, you see that this one is our like the circuit under test. So in that you have the chain. So usually we don't do one chain. That means you remember when I yeah, when I show like the scan chain, it go through the flop, but there's not only one, because if one imagine that you have a 200K flop, 200,000 flop, you should have one chain. It means that to go from the first flop to the 200,000 flop, it means it takes too much time. So one chain usually they do about like maybe a 100 flop or something. So you will have about thousand of chain like that, which is you have a thousand like this, right? You have thousands of them, which means you have a thousand of like input like this. So which is you have a thousand of like the vector of thousand bits like this going to. Because of it, it's like the huge, right? The huge of vector to fit into that thousand is a big number. So instead of fitting directly the data into here, with that, they will do like the compression and they do the decompression. So they will do like here, instead of thousand of chain like that, they go quite like apply only like let's say like tens, 100 of them, and what, and then they will have a decompressor. It will be like it's kind of like a demultiplexer, and then you have that like value become like thousand in here, and after you read the value, it will be compressed and then will read back. So this technique is like the new technique since I don't remember when, but it's like it allow to, that's like in the goal to optimize right time, because now you have like instead of one chain you have a multiple chain. Multiple chain, it means you have a big number of uh, like number of bit to fit in. Then you have to this one to reduce that. So that means that you have like the cost is you have to insert the logic here, the logic of the compressor and compactor, so that it like take care of the thing. But the thing is like you have a cost will be lower, because now the tester now have only like a hundred of bit to handle instead of thousand. So this one is that, so the key thing is like if the DFT is good or not, it will handle like those decompressor or compactor better or not. That's how the DFT is working. So the idea, right? So the idea, the simple idea is that you just reduce the number of bit in and out of the circuit. So that's one. This one is like the scan in and scan out. So let's go back to the this. Yeah. So with that, I think we done with the, yeah, we done with this. So those in built-in cell test. Built-in cell test. That's what the DFTs insert, right? Is that if the cell test, it doesn't mean that it can test by itself completely. Self test is just like give us the capability that reads the stimuli side, and then outside I think is you still need the tester to read the data out. Okay, then I think that'll be it. So any question? Oh yeah, that's question here. Oh yeah. By the way, okay, I think that's the end already. Oh, okay. A question from Anne. So what happened with the defective chips? You know, with the defective chip, throw away because it's defective, right? So cannot use. Defective means it is no longer function. So you or it function, but like it function like a unreliably. So it will operate not with the live, what not with the like it will fail sometime. There's a many level of failure. It fail randomly, or it fail completely, or it fail sometime in some scenario. All kind of thing is called failure. So when it fail like randomly, it's not used either. It cannot be it cannot be used. When it fail completely, it cannot be used obviously. But when it fail like just like randomly, it cannot be used either. So only like okay, they have to cover only 90 to 95%, but in the real life it won't be 90 to 95% because when they do that, they always do with some margin. So when they say 1995, maybe like they cover a lot, like the failure is not even 5%, it's not 10 5%. It doesn't mean the failure will be 10 or 5% in the real life because they build into the margin already, right? So even I do 90 to 95%, that's with the worst condition. But in real life, all the chip don't work at the worst condition at all the time, right? So which is like the chip can work at the temperature of the room temperature. Chip can work at the worst condition. So those chip might like be like vulnerable for those things. But in total, so you think that like 90% coverage, it might be have a 10% of failure, but it's not. It depends. If the yield is like when they yeah, the yield is okay. That's not gonna go to another. Okay, let's put it away. All right, the second one from Bao. Aside from testing the temperature and testing the voltage, what else will they test? Like the CPU, will they implement it into the real mainboard and test it? The tester will have that too. Yeah. Uh, Actually, I think it's not the real main board. Okay, first thing, temperature and testing voltage is not only temperature and voltage. What else will they test? Um, let's see, what else do they test? They test. They test with the I think with the ESD, which is like you have an electronic static, right? The ES like electronic static charge. So which is like will like they have some like model for the in case you have the lining, so it can still stand it, and you have because they will have the protection inside, so that like when you have lining, the high voltage like a 10K voltage, they test at beside. So that means that the failure that's by itself first. The condition is another one. I think there's a lot of like oh, they have also like the moisture too, but the moisture is like I don't know how they model that. They have I think they have more than that, but the three main thing they check they test is the temperature, voltage, and also the voltage like not only the operating voltage. They test the spike, which is like the lining. That's that one. And also they test. Oh yeah, they test also the mechanical. You remember like the Nokia cell phone previously? They will test for the mechanical, and then also the pressure because the chip when it come out they have to test for the pressure. Like if it changes, like the chip won't break. So a lot of things. So I don't know everything because it's in the fab, but the things we know is like what I presented. And then how they test the CPU. They will have the test board for the CPU. It's not exactly as I think it's similar to the main board, but it's not because the main board depends on like each vendor, right? So you have a Dell, we have a different main board than like the like a Gateway or like a Lenovo and so on. So So they have some kind of like a standard test board, so that they plug in, and then they will like test they will test with they but they need to verify, check all the um, sorry, this one is a test about like two things. We have a two things to test here. One is the failure, so that test failure is might not be like the same as the real ball, but the other one is functional test. That's this kind of similar to the real man ball. It's not the same real man ball because the man ball is different for each vendor. So here they will have the main thing is that they have the ball, so that they have that's with the tester, right? That's they have the tester, and they will have the ball. They plug the chip into the ball, and that ball is like compatible with the tester, and that ball will have all kind of like connections, so that allow the tester to like test inside. So I think it's not the same. When it tests for the failure, it will not be the same as the main ball, because here you can see that it fit into, right, the test pattern and the test the things like that. You have a those bus which doesn't exist in the main ball. So those tests, those test factor. Okay, I think Professor Tenera like announced the 10. So sorry, I think there's we still have a two more session, right? And I'm sorry that like I think it's late in the class that I want you to know one thing, or like I would like you to do thing. If you want to ask question, just speak that up, because usually I think I'm talking and I didn't pay attention to the message. You just like I have a question, and then just interrupt me anytime. But we have only two class left, two session left. So but just interrupt me anytime if you have a question, and yeah don't hesitate, just do it. And then like or like you can do this way. I can do this way. You write the question in the message, and then you raise your hand, or like you just speak up like, teacher, I have a question in the message to get my attention, so I will get to that. So it's better, because now I think it should happen. I thought that like I will ask you to do that, but I just forgot until now. Okay, so just okay. Briefly, next time if you want to ask question, write that to the message, and then like speak up. Like I have question in the message. I think that way will be quick, so that you can get the thing go on. All right. So yeah, I think okay. Back to the question from Anne. I think I want to talk a little bit more about that. Is usually when they take they test the ball, right? They test the chip and they test the ball. They test the chip. Sometimes like they test, as I said, they cannot cover 100%. So sometimes they miss it, but they accept it. That means like they accept that like they missed it, because the cost, you can see that the cost of like the efficiency, like it will go like this. Oh, everything's kind of going like that. So here, when we go like the yield until here is like really like you have the yield here, right? And the cost is here. So you got up to that is to work to the cost to get up the yield until here. Here's the yield, and here's the cost. So when it go up until here, it's worth the cost, because then the cost going up, but the yield going up too. Now if like if they get like, let's say 90% or 95% here. Now with that, now 5 or 10% left at the end here, to get to that, the cost is enormous. You have that, you increase, right? That means that here at least $1 a chip. This one you can cost $100 to test like a totally. With that, because of it, they don't want to test this portion. They don't want to go this. They just there, because they still know that like it's not like everything here will be fail, right? Will fail. So they will just like ignore this part. Sorry, where's my thing? Okay, here. Do you see my mouse moving, right? No, you don't see that. I think here. Yeah, here. So this part, they won't care. If like it fail, they will like replace. So that's why you see that like at Vietnam we try to fix here and here. Even for the ball, I think in here, if a ball fail, they just replace for you. They don't bother to fix it. Later on, I think because the cost of the ball is too much, so they have somebody to fix it, but they still they still still balance. Actually, they still balance between the cost to test and the efficiency. So they will like stop at something here. And whatever the defective chip, for sure, defective chip, throw away. The defective ball, because in that ball there's a many chip in there, so the defective ball they can reuse. Actually, they will redo the test. Like you see, they buy the iPhone, right? They buy the iPhone or they buy the Samsung phone, and then when it's failed, they can we send back. What they do with their phone, they will check first, and we check briefly. If the cost of debug repairing is too high, they throw it away. They don't bother to fix it. They just so you see that you have people buy the refurbished, right? The refurbished iPhone or something. Those things is has a very minor problem. Okay, this on the board there's something the connector is not very tight or something like very minor thing. So that means I do some cosmetic or some easy fix. If it require more than because the service here is costly, right, expensive, so anything require time to debug more than hour or something, they will not allow it. They just throw it away and then give new thing. So that's the way, because you can see that it looks like oh they just uh, waste the money, waste the ball, right? But it's not. I think here is the rule here is all about time. Time is money. So if you spend time to fix something, that means it costs, and it will balance with the cost of the because the chip is produced in mass, right? So each second there's 1,000 of chip coming out. But if you debug something, that's the manual, and that's the cost of, because the cost of even the technician here, they got maybe 40 or $50,000 a year, right? So that means 45. That means they salary about 50,000 a year. So that means that every hour is a $20 or $25 an hour. However, that's not all cost. If the company pay them $20, $25, it means they cost at least in the $50 or $100, about 2 or 3 times that. So which means if a technician have to sit there for 1 hour to fix the thing, it will cost them about $100 already. So they don't mind if if the chip is only $20 or $30, $50, they just okay, get a new one and then throw it away. So it's all about the cost. All right, so is there any scenario when the chip will be disposed, be in defective? It's a good question. Let's say when it's not defective. Okay, that's very good question. So it is like this. Usually, let's say you see the chip come out. You see that the frequency, right? The frequency is, you have a range. So you have the Intel CPU. Some is it has from 3 gigahertz, some from 2.5, some from the 2 gigahertz. So which means initially in the old days, the chip coming out if the vendor the Intel, they marketing that the chip working at 3 gigahertz. If it doesn't meet that frequency, so it's not effective, but it doesn't meet the frequency, then in that case they cannot sell at 3 gigahertz. So they have to use that for a kind of, they will sell that some kind of on sale with the less expensive. But nowadays, because all kind of things, those chips is too complicated, it costs a lot, so they cannot afford to throw it away. So now it's have a bin. which is they have a like if the chip they will rank it, they will like rank it like from 1 gigahertz, not one, like 1.5 and up, and they will rank it so that like every time like you have a, so the guys you need, if you need, because 1.5 gigahertz still working, still good, it's just like it's slower. So that means like this even it doesn't meet the requirement, but it's still like it still can be sold to the customer. So that means the one that's used to be like disposed, besides being defected, nowadays it's used too. Now let me think which one is can be like disposed between like beside the being defective. Uh, I don't think, I don't know. Okay, I don't know. It's just like it's not effective. They will use that even it didn't meet the requirement, because the thing is that we have to meet the performance, right? The trigger has the reason for that is because you meet that requirement. It means that you sell that for higher price. If the 3 gigahertz chip will be sold more expensive than the 2 gigahertz chip. That's all. So that means if you can meet the timing requirement, that means you can make a more expensive product, and you can make more money. That's all. What else? Maybe okay. Let me take this question to like ask around in my in my team. Okay, so not my team. My team maybe don't know, but I think the other team about like about the foundry. Yeah, the foundry team. That's a good question. Anything else? You're welcome, Bảo. All right. So, Professor, then I think if you have anything else to add.
No, thanks.
Yeah. Okay, then I think we can stop here, and thank you for your attention. And then like I hope that the stuck cat phone is not that I hope that it's not that confusing. I think you can figure it out. If not, just like ask me next time. Next time we have a two class yet left, right? So I think this will be the layout design, physical design. Um, the physical design, I think as a professor Ten talked about that, maybe could you like introduce to them like the program so that they know something, because you introduce that to the CC1, right? Or is that
Yes. Okay. So
do you want to share it with the class so that they are aware?
maybe next time, because now already over time. So
Okay. All right.
if they have another classes, maybe
Yeah.
no problem.
Okay.
Okay.
All right. Okay, so because it's just briefly, I think Professor and I introduced that like the I think the faculty, the department has been working with Renaissance and to introduce with like I think we will have the more tools, more software like about the SDA, DFT, and layout design, the PD, the physical design, which is very good because it's allow us to be able to like produce a chip, like go through the flow from the synthesis from RTL all the way through the GDS2, which is like to make a chip. The purpose is, I think Professor then will talk in detail. I just kind of talk briefly like that. I just mean that like we have a kind of very good like approach, like a roadmap ahead of us for this one. So it seems that the future is quite bright for this field. All right, so I think you will get to know like about that more next time. Okay, thank you everyone, and have a good weekend. Goodbye.
Okay. Thank you. Goodbye.
Bye then. Bye everybody.